All right, you crazy kids. Here's your lecture on equilibrium. Let's start with the equilibrium you are familiar with. Opposing forces are balanced. So in this little drawing here, why is it possible that this line is at a horizontal? Well, because this force is equal to this force, and therefore this line is nice and steady. Chemical equilibrium is a little bit different. So chemical equilibrium says the reactants and products have no tendency to change with time. What that means is that the concentration of your reactants and the concentration of your products are no longer changing. When I look at concentration, remember I'm talking about molarity here, so that's why I'm using the brackets here. All right. Initially, in any chemical reaction, you're not going to have any products, and you're going to have only reactants. So I have no products, and I have a whole bunch of reactants. Over time, what's going to be happening to your reactants? Well, they start changing into your products. So my concentration of my reactants is going to go down and eventually level out. My products is going to be the exact opposite. I'm not going to have any products, but then I'm going to make a bunch of products, and then the concentration is going to level out. It's going to stay at a steady. So, in terms of equilibrium, when you have your concentrations of your reactants and products staying the same, or if you're in this position right here, you have reached chemical equilibrium. The big part here is therefore the forward reaction proceeds at the same rate as the reverse reaction. Meaning, as your reactants change into your products are changing back into your reactions at the same rate. So, that means my reactants here are changing into my products, and my products here are changing back into my reactants. We haven't really talked about this so far, but basically every single chemical reaction is reversible. If I have A and B making C and D, believe it or not, while that's occurring, C and D are remaking A and B. That is a reversible reaction. Chemical equilibrium is when that rate of change is the same. Now, in chemistry, we care about the position of chemical equilibrium. To figure out the position, we calculate the equilibrium constant for the reaction, or the KEQ. The position of chemical equilibrium will tell us which is favored, either your forward or reverse reaction. That's kind of important when you are talking about chemical reactions. The more favored something is, the more important it is. For KEQ, we have this crazy calculation seen here. However, I've rewritten it in this format here to make it make more sense to you. So, if we look at our reactants, A and B, I now have concentrations A and B. I also have my coefficients A and B turning into exponents A and B. On the other side of my reaction, I have my products, C and D, now turning into concentrations of C and D. And I also have my coefficients C and D turning into exponents C and D. Let's practice this in real time. So here we are. We have this chemical equation. I'm going to write my KEQ expression, and that's very important because that's required, as HCl squared over H2 times Cl2. And just to run through it one more time, here we have our reactants as concentrations, and we have our product, and we have an exponent that was once a coefficient. I've listed all that information out for you there, and we can also see some important information about temperature. So first of all, KEQ is constant value for the system at equilibrium. So when your rate of change, forward and reverse, is the same, that's when we can calculate KEQ. And it is temperature dependent. So if I change the temperature, I'm going to change my KEQ. Okay, well, you're probably asking, well, what is this KEQ? What are we doing here? Well, you're going to be calculating a value. That value is going to tell us a lot of important things. If the value is greater than 1, we're going to have more products present in our actual system. So if this is my system, and I had A and B making C and D, if it's more than 1, I'm going to have a lot more C and D in my system. There's simply more of them, so they're a higher concentration. That means the reaction is going to favor the products. The bigger the value you get, believe it or not, the more favored it is. So if I was going to react something like zinc and hydrochloric acid, that reaction nearly goes to completion. When it's all done, there's no real zinc left. So that means that KEQ value is going to be very, very, very high. So I'm going to have way more products than reactants when the reaction is quote-unquote done. remember that there is no actual done in terms of chemical reactions. There's chemical equilibrium. If your KEQ is 1, that means the concentration of your reactants is going to be similar to your concentration of products. Not one side is favored. If your KEQ is less than 1, I'm going to have more reactants present in my system. That means the reaction is going to favor the reactants. And if it's really, 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 really small, that means the reaction doesn't really even occur. For example, if I was reacting gold and water, and I put some gold in water, it doesn't actually really react that much. There's going to be very, very few actual chemical reactions occurring. Most likely, you're going to just be left with gold and water. So you're going to have a way higher concentration of your reactants than your products, so your KEQ value is also going to be very, very, very small. A couple important things to note here. Brackets is concentration, so we're dealing with molarity. If we're dealing with molarity, hopefully you understand, I can only be dealing with really gases and aqueous solutions. A liquid or a solid doesn't really have a concentration. It's a constant concentration. It doesn't change. So the concentration of liquids and solids don't really exist, meaning they're not going to be part of your KEQ calculation. Let's look at your first example. So we have some nitrogen and hydrogen making ammonia, and we have the concentrations at equilibrium of these components of the reaction. So the reaction is at equilibrium, meaning it's quote-unquote done. Your forward and reverse reaction rates are the same. Now, for our expression, right? And then we're going to actually do calculation. Our expression is going to be your products over your reactants. So I'm going to have my NH3 squared over N2 times H2. And H2 is going to be cubed due to those coefficients. That's the expression that's required. And then you're going to plug in for your calculation. For my calculation, I'll have 0.113 squared over N2 concentration, which is 0.0602, times my H2 concentration, 0.420 to the third. Plug this in your calculator, and you guys should try this just to make sure you have the ability to, do this. You should get 2.86. You're going to love the fact that there is no unit to KEQ. It's simply a number. However, the number has significance. What does that number mean? Well, it's greater than 1, so your products are favored. Neat. Next, example 2. Now I've listed out the KEQ expression here. Why don't you guys take a look at it and see if it makes sense? Probably would need to pause here, but I'm going to continue on. It doesn't make sense because I have solids in my expression. That cannot happen. They don't have concentrations. Those should be removed from my KEQ expression. They should not belong there. I should really just have my copper nitrate and my silver nitrate present. These other things do not belong. All right, now that we have the expression taken care of, let's take a look at our calculation. We're going to have our concentration of copper 2 nitrate, and that's 12.3. No coefficient, so no exponent, over my concentration of silver nitrate, that's 3.2. And that's going to be squared due to the coefficient. You plug that into your calculator, we get a value for your KEQ as 1.2. That 1.2 tells us, wow, it's really close to 1. So in this case, my products are slightly favored. And that is equilibrium. Good luck.